Here is a combined summary of pages 3 and 4 of the research paper. The paper addresses the problem of application usage prediction, where the goal is to develop a predictive model that can accurately predict the next application a user is likely to use. The problem definition and relevant feature data for app usage prediction are illustrated in Figure 1, which includes various feature data types such as application sequence, user IDs, timestamp sequence, base station ID, and points of interest (POI) data. The paper identifies limitations of existing work in application usage prediction, including inadequate representation of core data, oversimplified or overly complex data fusion strategies, and limited capabilities of feature extraction networks. To address these issues, the paper proposes a new system that can improve the accuracy of predictions and user experience. The dataset used in the study is a real-world application usage dataset collected from Shanghai, China, during a week-long period from April 20 to April 26, 2016. Each dataset entry contains an anonymous user ID, a timestamp, a base station ID, and the ID of the app being used, organized chronologically by timestamp. The POI data, indicating the presence of different facilities near a base station, plays a vital role in defining the functionality and appeal of specific locations. The data preprocessing for app usage prediction is illustrated in Figure 2, which includes the implementation of word embeddings, the application of clustering techniques to points of interest (POI) data, and the encoding of temporal data. The app sequence is transformed into a continuous vector space using word embedding techniques, and the POI information associated with base stations is used as input for location features. The paper introduces the Appformer framework, which consists of two primary components: the Multi-Modal Data Progressive Fusion module and the Feature Extraction module. The Appformer framework is designed to effectively leverage the rich, interconnected data, enhancing its predictive accuracy for upcoming application usage. The mathematical representation of the predictive model is illustrated by equation 1, which represents the next application a user is likely to use based on a multidimensional feature sequence incorporating essential historical data. In this paper, the authors propose a novel framework for predicting mobile app usage sequences, leveraging multimodal data such as app usage history, user demographics, points of interest (POI), and time data. The proposed framework, named Appformer, consists of two core components: the Multimodal Data Progressive Fusion module and the Feature Extraction module. The Multimodal Data Progressive Fusion module is designed to integrate data from diverse sources effectively and discern the importance of varying data types. It utilizes cross-modal attention mechanisms and progressive fusion strategies to merge encoded app vectors, user vectors, POI vectors, and time vectors step by step. The cross-modal data fusion module, inspired by the decoder module in the transformer, integrates operations such as multi-head cross-modal attention, masked multi-head self-attention, residual connection, and layer normalization, feed-forward. The feature extraction module is responsible for extracting relevant features from the fused data to enhance the predictive model's accuracy. It comprises an encoder and a decoder, which work together to process the input data and generate predictions. The authors also compared different clustering algorithms for processing POI data and find that K-modes achieves the best result. The paper demonstrates the effectiveness of the Appformer framework in predicting app usage sequences, showcasing its potential in enhancing user experience and optimizing app development strategies. Algorithm 1, Appformer, integrates a multimodal data progressive fusion module and a feature extraction module to process mobile app usage data. The fusion module combines app, user, POI, and time vectors through a series of linear transformations and cross-modal data fusion operations. The feature extraction module employs an encoder-decoder architecture, inspired by the transformer, to capture complex relationships within the data. The encoder processes the fused multimodal data using multi-head self-attention and feed-forward networks, while the decoder decodes the high-dimensional representation and combines it with a conditional vector to produce the target sequence. Table 3 compares existing data fusion methods for mobile app prediction, highlighting their limitations and applicability. NAP and Deep App directly concatenate heterogeneous raw data, overlooking data relationships and relevance. App Usage 2 VEC integrates user and app data through a Hadamard product, capturing interactions but overlooking complex data interactions. DUGN utilizes an interest fusion layer to capture dynamic user preferences, adapting to real-time changes but struggling with noise and interest changes. Table IV compares feature extraction methods for mobile app prediction, highlighting their limitations and applicability. NAP uses LSTMs, excelling at handling sequential data but struggling with multimodal data. Deep App employs multiple GRUs, efficiently analyzing concatenated data but struggling with deep temporal dependencies. PAULCI combines GRU networks with an attention layer, selectively focusing on informative parts of the data sequence but missing key features in complex multimodal inputs. App Usage 2 VEC uses dual DNNS, independently extracting user and application features but overlooking complex multimodal interactions. DUGN utilizes a combination of temporal gating mechanisms, hierarchical graph attention networks, and self-attention mechanisms, effectively capturing user preferences but relying on data quality and limited by fixed structure. The proposed feature extraction module addresses these limitations by adopting an encoder-decoder architecture, introducing attention mechanisms, and designing modular and replaceable feature extraction methods. The module leverages a combination of multi-head self-attention and feed-forward networks to capture dependencies within the data, and the interaction between the encoder and decoder is facilitated through the cross-modal data fusion module. In this paper, the authors propose a novel cross-modal data fusion module for enhancing the performance of next app usage prediction. This module is designed to leverage both app and point of interest (POI) data to provide a richer and more comprehensive feature vector for the prediction task. The authors demonstrate the effectiveness of their approach through a series of experiments, comparing their method with several baselines and state-of-the-art models. The proposed cross-modal data fusion module utilizes a combination of multi-head self-attention and cross-modal attention mechanisms to effectively integrate app and POI data. The authors also employ a feed-forward network to further process the fused features. The output of the fusion module is then fed into a decoder for generating the final prediction. The authors conduct a thorough evaluation of their approach using various metrics such as hit at K, MRR at K, NDCG at K, and F1 score. They compare their method with traditional machine learning classifiers like random forest, logistic regression, and XGBoost, as well as advanced deep learning models including MLP, LSTM, GRU, and others. The experimental setup includes parameter settings for sequence length, embedding dimensions, and framework configuration. The authors also discuss the importance of data cleaning and partitioning, adopting different methods from PAULCI and DUGN for comparative experiments. Overall, the paper presents a novel approach to enhancing next app usage prediction by leveraging cross-modal data fusion. The proposed method shows promising results compared to existing baselines and state-of-the-art models, demonstrating the potential of integrating app and POI data for improved prediction performance. The research paper presents a comprehensive analysis of mobile app usage prediction, focusing on the development of a novel model named Appformer. This model integrates various types of data, including user information, spatiotemporal information, and historical app sequences, to enhance prediction accuracy. The authors compare their method with other state-of-the-art methods, such as PAULCI and DUGN, and demonstrate that Appformer achieves superior performance across various metrics. A detailed ablation study is conducted to investigate the key components of Appformer. The results show that the time encoding and fusion methods, as well as the clustering operation of POI data, play significant roles in enhancing spatial information and capturing the inherent patterns of time information. Furthermore, the authors compare different time encoding methods and find that their proposed improved method outperforms the basic method. The paper also explores the input to the decoder in the Appformer model, revealing that feeding only POI data into the decoder yields optimal results. This is because the user sequence itself consists of repetitive numbers, and the time series changes slowly, making redundant data potentially interfere with the decoder's decoding operation. Additionally, the authors conduct a feature extraction module comparison experiment by replacing the components in the feature extraction module of Appformer with equivalent modules from Autoformer, Fedformer, and Quatformer. However, the results do not meet expectations, possibly due to these modules being primarily designed for long sequence prediction tasks and not fully adapting to the characteristics of the short sequence prediction task. Finally, the paper presents clustering experiments on POI data with different cluster sizes, aiming to determine the number of clustering centers and select the best clustering method based on the number of centers. The results indicate that the optimal number of centers is 30, as it achieves the highest performance metrics. Here is a combined summary of pages 13 and 14 of the research paper. Determining the optimal number of cluster centers is crucial in clustering POI data, as it guides the selection of cluster quantities and methods. To achieve this, the authors employed the basic k-means algorithm in combination with Appformer for the cluster center comparison experiment. The experimental results, as shown in tables 11 and 12, demonstrate that the optimal number of clusters for POI data is 5, based on hit at 1, hit at 3, hit at 5, MRR, and F1 score. However, the relationship between the number of clusters and performance is not simply linear, with performance generally declining as the number of clusters increases from 5 to 55, albeit with some fluctuations. The authors also tested different clustering methods, with experimental results indicating that the K-modes algorithm demonstrates superior performance in terms of hit at 1, MRR, and F1 score. Visual analysis using principal component analysis, PCA, revealed that some data points significantly deviate from the central region of the overall data, identified as noise points. The K-modes and mini-batch K-means algorithms can effectively recognize and disregard these noise points, assigning them to the nearest cluster, thereby minimizing the adverse impact of noise on the clustering outcome. In contrast, algorithms such as K-means, K-means++, and K-harmonic means incorrectly identify these noise points as cluster centers, which is suboptimal. The K-modes algorithm is more rational and effective in selecting cluster centers, ensuring they are located in the true core areas of the data, thus enhancing the accuracy and reliability of the clustering results. Through the clustering analysis of POI vectors, the K-modes algorithm exhibits significant advantages in handling noise, maintaining data centrality, and improving clustering accuracy. These findings not only validate the effectiveness of the experimental results but also provide valuable references for future clustering analyses on similar datasets. This section of the research paper presents a comprehensive list of references related to mobile app usage prediction, multimodal learning, and various machine learning techniques. The references span multiple fields, including human-computer interaction, data mining, and artificial intelligence. The authors have cited works from esteemed researchers and institutions, demonstrating a thorough understanding of the existing knowledge in the field. The references cover a range of topics, including mobile app classification, app usage prediction, multimodal learning, and deep learning techniques. They also touch upon various machine learning algorithms, such as support vector machines, random forests, and neural networks. The authors have also cited papers on word embedding, attention mechanisms, and transformers, highlighting their relevance to the research. Some notable references include works on mobile app recommendation systems, such as Deep Sense and NAP, which utilize deep learning and natural language processing techniques to predict user behavior. Other references focus on multimodal learning, including papers on multimodal transformers and attention-based models for multimodal sequence fusion. The authors have also cited papers on various clustering algorithms, such as K-means and K-modes, which are essential for identifying patterns in mobile app usage data. Additionally, references on long short-term memory, LSTM, networks and gated recurrent units, GRUS, demonstrate the author's understanding of recurrent neural networks and their applications in time series forecasting. Overall, the references provided demonstrate the author's thorough knowledge of the existing literature in mobile app usage prediction, multimodal learning, and machine learning techniques. The cited works will likely serve as a foundation for the author's research, providing a solid basis for their proposed approach.